astronomers have recently stumbled upon a phenomenon that defies all expectations. At this very hour, 7 separate comets are hurtling inward, converging on the Sun with uncanny precision, each destined to arrive within mere days of one another in October 2025. In the long record of human observation, no such convergence has ever been seen. Yet what transforms this event from extraordinary to deeply unsettling is the presence of another visitor. 3 I divided by Atlas, a wanderer not of our solar system but of distant stars, drawing near in that very same narrow window of time. The probability of such overlapping arrivals is so vanishingly small that chance alone seems an insufficient answer unless, perhaps, some hidden mechanism binds them together. Could it be that what we are witnessing is not a harmless passage, but the opening act of something darker, something deliberate? Tonight we set out to examine every possibility, exploring the edges of science and venturing into realms of speculation where unseen forces may be at work. Remain with us, for by the end we will confront the pressing question: what is 3 I divided by Atlas truly doing within our solar system? In an ordinary year, the heavens might grant us 1 notable comet, perhaps 2 if fortune is generous. Many cycles slip by with nothing more dramatic than faint smears of light in the telescope, small victories cherished by the most devoted comet chasers. Yet the year 2025 is different. It feels less like the random rhythm of the skies and more like a procession arranged upon a grand celestial stage. 7 radiant travelers are stepping into view: Pan, Stars, Swan, the Solar Terrestrial Relations Observatory Comet, Atlas K1, Atlas G3, Lemon, and the Near-Earth Asteroid Tracking Discovery. Each carries within its icy heart the ancient memory of the solar system's distant borders, yet all arrive within mere months of one another, as if the universe had scripted a reunion no one had planned. Imagine 7 friends, scattered across a vast country, arriving at your door on the same weekend, each insisting they never knew the others would appear. Possible? Certainly. Coincidental? Likely. But strange enough to suggest hidden invitations whispered in secret. Without question. Astronomers describe this clustering with a term, the swarm effect, when multiple comets gather into a compressed observational season. From Earth, the convergence appears almost choreographed, as though unseen forces had shepherded them here together. Before we follow this trail further, it is worth establishing our vocabulary. Perihelion marks the instant when a comet draws closest to the Sun, when the frozen vaults of its surface erupt into radiant tails of gas and dust. Closest approach describes the distance between comet and Earth, deciding whether we must reach for telescopes, lift binoculars, or simply gaze upward with bare eyes. Magnitude is the astronomer's measure of brightness. The lower the number, the greater the glow. A magnitude of 6 flirts at the edge of human sight beneath the darkest skies, while magnitude 0 rivals the great stars themselves. Now imagine the data displayed as a chart. In most eras, dots of cometary arrivals scatter across decades like raindrops spattered upon stone. Yet 2025 shows 7 points crowded close, a handful of marbles dropped together at once. Amateur astronomers, accustomed to spending entire seasons chasing a single dim visitor, suddenly find themselves overwhelmed with choices. Photography forums overflow with images capturing several luminous tails sweeping the same swath of night. Social media ignites with time-lapse reels, recording what appears less like chance and more like a ballet rehearsed in the vault of heaven. And yet, there is another presence, something stranger, more unsettling. Moving silently beyond the orbits of these familiar comets, drifts an object from elsewhere. 3 I Atlas, the 3rd interstellar body ever confirmed within our solar system. Unlike the 7 icy wanderers, this Voyager was not forged in the primordial cradle of our Sunday. Its birthplace lies around another star entirely, and its trajectory through our system is a one-time passage, hyperbolic, destined never to return. The timing gnaws at the minds of astronomers. Is this season of abundance no more than coincidence? Or does the arrival of this alien traveler hint at an orchestration yet unseen? Throughout this inquiry, we must tread carefully between the firm ground of measurement and the shadowed terrain of speculation. Orbital charts, observation logs, and brightness records are facts one may trust. When we step beyond these numbers, we must mark our words clearly as conjecture. The method is simple yet uncompromising. If 3I Atlas is in any way connected to the convergence of 7 comets, the relationship must leave visible traces. Correlations of timing too precise to be chance. Orbital alignments that defy randomness. Interactions that instruments can capture and verify. We are not in pursuit of mirages, nor of imagined shapes in clouds. We are searching for evidence so tangible that even the most cautious skeptic would be compelled to agree. The consequences extend far beyond mere curiosity. Should these 7 comets prove to be independent travelers, obeying only the mathematics of celestial mechanics and the impartial discoveries of survey telescopes, then what we are witnessing is a rare but natural convergence. The cosmos is vast enough to deliver coincidences that feel charged with meaning, though they are not. But if some external force, whether gravitational, electromagnetic, or a phenomenon beyond today's physics has nudged these wanderers into synchrony, then we may be staring at influences on scales barely comprehended, forces capable of reshaping our understanding of movement through the void. 7 comets do not simply gather in the same season without cause. Within a solar system ruled by the steady mathematics of celestial mechanics, every orbit becomes a testimony, every trajectory a record etched by invisible forces. If some guiding hand has steered these objects into their present courses, then the evidence of that influence should linger like fingerprints upon glass. Into this picture enters the interstellar traveler, a wanderer carrying its own enigma. 3I Atlas bears within it ancient ice and dust, matter, once kindled in the furnaces of a distant star, altered through eons of cosmic radiation during a voyage that likely stretched across millions of years. Locked in its chemistry are messages about the birth of worlds beyond our own, and in its reactions to the heat of our sun lies the key to understanding how foreign materials respond under familiar fire. Yet the unsettling question arises: what if this passage is not random? What if the same unseen force that may have nudged 7 native comets towards synchrony also summoned an interstellar visitor, timing its arrival with eerie precision? Such speculation multiplies like fractals, each possibility dividing into countless new questions. How might we detect such an influence? What mechanism could act across gulfs of space so wide that light itself requires centuries to cross? And if such orchestration exists, what truth does it whisper about the deeper architecture of our cosmic neighborhood? As we turn toward the 7 icy emissaries converging upon our skies, we must hold close the reminder that the universe seldom unveils its mysteries without resistance. Every genuine discovery begins as an observation that refuses to conform to the model. Every true breakthrough springs from the moment someone dares to ask why the familiar is not behaving as expected. The swarm has arrived, and with it comes a tide of questions that may challenge the very framework through which we interpret our solar system. Now the task before us is clear. We must meet these 7 travelers not as curiosities but as carriers of data, each one a thread in a larger tapestry. Whether their convergence is coincidence or connection remains to be seen. The evidence waits in their orbits, their light, their chemistry. The time has come to measure. Let us meet our 7 visitors one by one, for each arrives carrying a unique tale of discovery and cosmic wandering. Imagine this as a lineup where every suspect insists on an alibi, and yet, somehow, all appear together at the same mysterious scene. The first to step forward is Pan-STARRS, the brightest among them, and the figure that takes center stage. This comet was discovered by the Panoramic Survey Telescope and Rapid Response System, a powerful Hawaiian sky patrol that has transformed the practice of comet hunting. Early predictions suggest that Pan-STARRS may become visible to the naked eye for observers across the northern hemisphere. Its window of brilliance stretches from late March through May of the year 2025, offering months of opportunity to study its approach. Yet it is not only the brightness that intrigues astronomers, but also the geometry of its orbit. The path runs close to the orbital plane of Earth, ensuring that its passage will be easily observed from densely populated latitudes. To minds attuned to patterns, this accessibility feels almost too convenient, perhaps uncomfortably so, for an object that supposedly drifts in by pure chance from the remote reaches of the Oort cloud. Next comes Swan, whose discovery story unfolds differently. The Solar Wind Anisotropy satellite was designed not to hunt comets, but to study the streams of charged particles flowing from the Sunday. Yet its hydrogen-sensing instruments inadvertently revealed a new role, capturing the distinctive glow of cometary atmospheres. Swan comets often burst into awareness suddenly, their hydrogen emissions betraying their presence before optical telescopes can react. This signature tells us much about the level of activity. Unlike inert rocks that only awaken under solar heat, Swan was already shedding gas when first observed, perhaps for months or even years, producing a vast envelope of hydrogen that gave it away. For a body said to follow a random orbit, it seems remarkably prepared for its entrance. The tail of the Solar Terrestrial Relations Observatory comet, often shortened to STEREO, is more dramatic still. Solar watching spacecraft, tasked with monitoring the activity of our star, glimpsed the comet rushing sunward at the edge of their vision. Many stereo comets become suicidal grazers, plunging perilously close to the sun, where they either disintegrate in bursts of brilliance or emerge profoundly changed. What heightens suspicion here is timing. Stereo's arrival coincides with a period of solar maximum, when the magnetic field of our star churns with turbulence. Is this pure coincidence, or does the heightened energy of solar maximum somehow draw distant objects inward? The correlation seems too precise to dismiss entirely. Then there is Atlas K1, a comet that once carried the weight of both hope and disappointment. When the Asteroid Terrestrial Impact Last Alert System first detected it, predictions suggested it could blaze as one of the most spectacular comets in generations. Reality, however, proved more modest. Most observers will require binoculars or small telescopes to enjoy its presence. Yet suspicion lingers, for its discovery date lies squarely within the timeline of the swarm, even though its orbital path implies a journey repeating over thousands of years. Why did we find it now? Why during the very year when so many others appear together? Atlas G3 follows, a sibling discovered by the same Hawaiian survey. The Asteroid Terrestrial Impact Last Alert System functions as a planetary guard, scanning the skies every few nights for moving points of light that could signal danger. Its success has been remarkable, yet therein lies the puzzle. A significant number of the recent comets in this unusual cluster owe their discovery to Atlas. This does not point to failure, quite the opposite. It proves the survey's cutting-edge power. But when the same system identifies multiple members of a sudden swarm, patterns begin to whisper that demand closer scrutiny. Comet Lemon enters our gathering from a lineage steeped in patient observation. It was brought to light by the Catalina Sky Survey Station on Mount Lemmon in Arizona, a program that has been scouring the skies for near-Earth objects since the 1990s. Over decades, this survey has built one of the most expansive and detailed archives of small solar system bodies ever assembled. Discoveries tied to Mount Lemmon carry with them the weight of long practice and careful calibration, though expectations for its brightness remain modest, likely requiring binoculars to appreciate its placement within the sequence of arrivals, is what makes it compelling. Lemon drifts into the middle of the formation, neither leading nor lagging, almost like a carefully positioned placeholder. Its mathematical neatness feels too precise, too aligned, to be explained entirely by random orbital chance. Our seventh visitor, the Near-Earth Asteroid Tracking Comet, arrives with a note of irony. The Near-Earth Asteroid Tracking Program ceased operations in the year 2007, yet discoveries made during its active years continue to reach us on schedule, tracing orbits first calculated decades ago. The Near-Earth Asteroid Tracking Comet stands as testimony to the endurance of systematic sky surveys, proof that patient vigilance yields results even long after the instruments have fallen silent. What makes its role in this gathering significant is the remarkable span of time between discovery and appearance. For more than 15 years, astronomers have followed its track, refining its orbit through thousands of recorded observations. There is no ambiguity in its path, no question about its timing. It was always destined to arrive in the year 2025. What raises eyebrows is not its certainty, but the company it keeps. 6 other comets arriving in the very same window. When all 7 orbits are laid upon a single timeline, the convergence is impossible to ignore. These are not comets stumbled upon in the year of their visibility. They were found across different decades, by different surveys, through methods ranging from hydrogen emissions and solar monitoring to asteroid patrols and dedicated comet hunts. Yet here they are, all crowding into one slender slice of time. It feels almost as if the universe had scattered the clues deliberately across many techniques, ensuring that eventually we would recognize the pattern. The statistics underline the mystery. Normally, comet discoveries scatter in random distribution, with rare bursts that seldom include more than 2 or 3 arrivals close together. 7 converging within months is a statistical outlier that begs for explanation. And yet, every orbit follows the strict dictates of gravitational mechanics, calculated with precision and verified through long observation. These trajectories were set millions of years ago, when the comets began their long descent toward the inner solar system. The question that lingers is stark in its simplicity. What started them on these paths with such uncanny coordination? What influence could act across such vast distances and timescales to bring 7 distinct bodies into synchronized arrivals? We are not declaring orchestration, only noting that the pattern is strange enough to investigate. For while each comet is behaving exactly as the laws of motion demand, together they seem to whisper of something greater than coincidence. But before we can consider any link to the interstellar wanderer, we must first ask, why does this particular clustering strike seasoned astronomers as so unusual? To answer that, we need to compare it with the rhythm of ordinary comet years. Step into any planetarium during a typical year and ask about visible comets. The resident astronomer will likely sigh, consult the records, and point you toward a faint, marginal object, one that demands a strong telescope and the darkest skies to glimpse. With luck, there may be a comet bright enough for binoculars, followed by long months of silence. In truth, most years pass without a single comet bright enough for the naked eye to grace our skies. Such is the baseline reality of comet watching. Long stretches of patience punctuated by disappointment, with rare rewards that require serious equipment to appreciate. For the wider public, comets remain distant myths, half remembered from history books or exaggerated in disaster films. The year 2025 breaks this pattern with the subtlety of a cosmic hammer. 7 notable comets arrive within mere months of one another. Several are bright enough to be photographed by ordinary cameras. Some will be visible through binoculars, and at least one carries the promise of dazzling the unaided eye. To grasp how unusual this clustering is, we must turn to the mathematics of discovery and visibility. Modern survey programs have revolutionized detection, but they have not altered the physics that governs comet brightness. The Panoramic Survey Telescope and Rapid Response System, operating from the summit of Haleakala in Hawaii, scans the accessible sky every few nights. The Catalina Sky Survey in Arizona sweeps different regions with relentless precision. The Near-Earth Object Wide Field Infrared Survey Explorer, a space-based infrared telescope, identifies the faint heat signatures of objects invisible from the ground. Together, these surveys discover hundreds of comets and asteroids each year, yet the vast majority remain forever faint, destined only for telescopic observation. Only a handful brighten enough to capture the public's imagination. Statistically, the expectation in any given year is 0 to 1 comet bright enough for naked eye viewing, with perhaps 2 or 3 more within reach of dedicated amateurs. But improved instruments do not explain the richness of 2025. Surveys may find more total objects, but the fraction that evolve into spectacular displays remains historically consistent. Detection does not create brightness. A comet's brilliance depends on its size, composition, and the geometry of its approach to the Sun, characteristics determined millions of years ago when gravitational nudges first set their long courses inward. Survey telescopes simply announce the inevitable arrivals. This distinction is vital. If better tools alone were responsible, similar clustering should have appeared in other recent years as technology advanced. Instead, 2025 stands apart as an anomaly, a year dense with activity. And while media coverage sometimes inflates modest prospects into disappointment, the reaction of seasoned comet watchers cannot be dismissed. They know the scale of brightness. Magnitude 6 marks the threshold of naked-eye vision under the purest skies, while suburban observers often require magnitude 4 or brighter. They also know the unpredictability of comet behavior, how a nucleus rich in volatile ices may erupt suddenly into brilliance, or how a dust crust may smother activity, leaving the object dim. Even so, intuition matters. Experienced astronomers, veterans of countless faint wanderers, are startled by this year's crowded schedule. Their surprise carries authority, the weight of decades spent tracking ghostly smudges across forgotten corners of the sky. And layered upon this anomaly is another element, the approaching peak of solar maximum, a cycle of heightened solar activity that may further complicate the tale of this extraordinary year. Our Sun lives by rhythm, pulsing through an 11-year cycle of activity. In quiet phases, sunspots nearly vanish, and the surface seems calm. In active phases, storms erupt with violence, solar flares bursting outward, coronal mass ejections surging into space, and magnetic fields twisting in chaos. The year 2025 coincides with solar maximum, the point of greatest turbulence in this repeating cycle. During such a season, solar storms can transform the appearance of comets, tearing their tails apart in dramatic disconnection events, or bending them into unusual shapes that exaggerate their presence. The strengthened solar wind enhances ion tails, rendering even modest visitors more photogenic than they might appear during solar minimum. Yet there is an important boundary to remember. Solar activity does not create comets. It only alters their display once they have entered the inner solar system. These 7 bodies were already destined to arrive in 2025, regardless of whether the Sun whispered quietly or raged with fury. Solar maximum might intensify the show, but it cannot explain why so many have chosen the same curtain call. Here the story turns inward, to human perception. Our minds are wired to seek patterns, a trait that once served survival. Detecting rustling in the grass as a potential predator was safer than dismissing it as wind. This instinct, sharpened over millennia, now compels us to read significance into events that may, in truth, be random. Clusters capture our attention, and when multiple rare events happen together, we hunger for explanation. The spectacle of 7 comets arriving within months of each other ignites precisely this response. To our intuition, such timing feels choreographed. Probability whispers that coincidences happen, but instinct insists that something must be guiding the hand of fate. Statistical truth, however, tells a colder story. Random distributions often produce clusters. Flip a coin long enough, and improbable streaks of heads or tails will appear. The human mind recoils from this inevitability, struggling to accept that order can emerge from chaos without cause. The challenge of our investigation, then, is separating genuine anomalies from clusters that fall within normal variation. For this, mathematics must override instinct. The key lies in orbital analysis. If our 7 comets reveal shared gravitational signatures, if they trace back to similar regions of the Oort cloud, or if their perturbations suggest a synchrony beyond chance, then suspicion of external influence gains strength. If, instead, their alignment fits within the statistical quirks of randomness, coincidence remains the soundest conclusion. The standard must be exacting, for extraordinary claims demand extraordinary proof. To suggest that some unseen force herded 7 comets into 1 year of arrival is a claim of rare magnitude. one that would shake the foundations of astronomy. Only evidence so strong it silences skepticism can support it. Yet the cosmos has a habit of humbling certainty. The universe occasionally presents surprises that no equation had predicted, revealing truths where once we saw only coincidence. The swarm is real, its timing is unusual, and the questions it raises cannot be ignored. What kind of force could coordinate objects across distances measured in light years and timescales of millions of years? And might the arrival of the interstellar Voyager, 3I Atlas, offer the missing piece to this enigmatic puzzle? When astronomers confront patterns that resist explanation, they reach instinctively for two familiar forces, gravity and electromagnetism. These twin rulers govern nearly everything that moves through the heavens, from the sweeping arcs of planets to the shifting shapes of comet tails. If something has drawn 7 comets into apparent synchrony, it must work through one of these channels. Gravity is the natural starting point, for it is the undisputed architect of the solar system. Every object with mass bends the fabric of space-time around it, weaving invisible currents that direct planets, asteroids, and comets alike. Its reach is infinite, and its mathematics precise, enabling astronomers to forecast eclipses and alignments centuries ahead. Yet gravity carries a paradox. It is universal, but astonishingly weak. Only immense bodies produce gravitational effects detectable across the gulfs of interplanetary space. The Sun dominates with overwhelming authority, its pull shaping the broad choreography of motion. Jupiter, though only 1,000th the Sun's mass, still exerts sufficient influence to sculpt the asteroid belt, capture swarms of Trojan companions, and redirect comets on new paths. For any hidden body to shepherd 7 comets into coordinated arrivals, it would need a mass comparable to a major planet. This is not a matter of subtle nudges unfolding over millions of years, but of powerful tugs that orbital models would immediately reveal. A comet's orbital elements, its inclination, eccentricity, and period carry a record of every gravitational hand that has touched it. These fingerprints cannot be disguised. If such a massive agent exists, its influence would echo clearly across the data. Jupiter itself demonstrates this principle, its gravitational signature evident in resonant gaps and captured families that can be mapped and predicted with precision. Thus, any hypothetical shepherd must leave behind similar orbital imprints. Their absence would dismiss the gravitational hypothesis. Electromagnetism offers an alternative, though one equally constrained. As solar radiation ionizes a comet's gases, the resulting charges respond to magnetic fields. The solar wind, an endless tide of charged particles streaming from the sun, bends ion tails, sometimes severing them entirely in dramatic disconnection events. But here lies the distinction. Electromagnetic forces shape appearances, not trajectories. They twist tails, not paths. A comet continues to move along the gravitational route fixed long ago, indifferent to the flickering of magnetic storms. For 7 comets to be guided into simultaneous arrival by electromagnetic means would require fields of unimaginable power on scales observed only near neutron stars or black holes. The energy demands would dwarf even the sun's radiance, and such manipulation would not pass unnoticed. Spectral signatures and tail anomalies would shout their presence to every observatory on Earth. This brings us to the essential line between speculation and science. Real shepherding, whether gravitational or electromagnetic, must leave evidence, shared orbital elements pointing to a common source, synchronized perturbations beyond chance, anomalies repeated across multiple objects, with a consistency that cannot be explained away. These are the criteria by which extraordinary claims must be tested, and with them in hand, we can begin to examine our 7 visitors, searching for proof or its absence in their celestial fingerprints. Pan stars, Swan, the Solar Terrestrial Relations Observatory Comet, Atlas K1, Atlas G3, Lemon, and the Near-Earth Asteroid Tracking Discovery share certain orbital characteristics that, at first glance, invite questions about common influences. Could their paths have been sculpted by forces beyond the standard gravitational environment of the solar system? The preliminary answer may disappoint those drawn to hidden orchestrations, yet it reassures the discipline of conventional physics. Each of these comets moves along a course entirely consistent with independent evolution under known gravitational laws. Their origins, inclinations, and timing patterns reveal no signs of coordination beyond the sort of statistical clustering that random chance can occasionally produce. Pan-STARRS approaches from a direction entirely unlike SWAN. The Solar-Terrestrial Relations Observatory comet dives perilously close to the Sun, while Atlas K1 travels along a far more distant route. Lemon and the Near-Earth Asteroid Tracking Comet trace their origins to different stretches of the outer solar system, following unique trajectories toward the inner regions. Were some hidden shepherd orchestrating these arrivals, we would expect to find subtle but measurable correlations, shared orbital nodes, common perturbations, or timing relationships that surpass reasonable coincidence. Instead, we observe 7 solitary travelers, each with a distinct path, converging only in the sense that their brightest phases happen to unfold within the same narrow season. Their orbits tell stories of isolated journeys, shaped solely by solar gravity and the occasional planetary encounter. This does not entirely dismiss the notion of coordination, but it raises the evidentiary threshold dramatically. If something is guiding these comets, it does so with mechanisms so delicate that current instruments cannot yet perceive them. The more straightforward explanation remains: statistical clustering, amplified by the reach of modern sky surveys. Yet, the investigation takes a fascinating turn when we bring the interstellar wanderer, 3I Atlas, into the frame. Unlike the 7 familiar comets, this visitor is not bound by the gravitational architecture of our solar system. Its hyperbolic trajectory and distant birthplace mark it as a true outsider. Could such an interstellar object, despite its small mass, play some role in the timing or behavior of local comets through processes we do not yet understand? Its limitations as a shepherd are immediately apparent. Its mass is far below planetary scales, rendering gravitational influence negligible. Its swift passage allows little time for cumulative perturbations. Its trajectory does not intersect directly with any of the 7, eliminating the possibility of close encounters. And yet, the timing unsettles. During the very year our skies grow more crowded with comets than in living memory, an interstellar guest appears. Coincidence? Perhaps, but a troubling one for those who resist mysterious alignments. The question is not whether 3I Atlas exerts invisible tractor beams or violates known physics. Rather, could its arrival correlate with natural conditions that favor cometary activity or enhance discovery rates? Perhaps 3I Atlas serves as a kind of cosmic weather vane, its presence coinciding with broader stirring in the outer solar system, a stirring that sends multiple comets sunward. Interstellar visitors may preferentially appear during epochs when such gravitational shifts are underway, offering not causation but correlation. These possibilities are speculative, yet they invite serious study. History has shown that the universe delights in weaving subtle connections that seem impossible until revealed by sharper instruments and deeper analysis. As we turn now to consider this interstellar suspect in full, we should remember: the most profound revelations often begin with observations that defy neat explanation. What once appeared impossible may simply be waiting for our understanding to catch up. The signal we raise is not the shrill cry of imminent disaster, but the steady call of scientific curiosity confronting an enigma. Think of it less as a fire siren and more as a cosmic smoke detector, an instrument that alerts us to something unusual in our celestial neighborhood, demanding careful examination before conclusions are drawn. The year 2025 promises a spectacle capable of transforming casual stargazers into devoted comet hunters. Multiple brilliant objects will unfurl luminous tails at once, producing photographic opportunities that occur perhaps once in a generation. Social networks will overflow with time-lapse sequences of celestial travelers sweeping across star fields with an elegance that appears almost choreographed. The show itself carries no threat. Comets are fragile bodies, loose gatherings of ice, dust, and organic material bound by only the faintest gravity. When solar heat sculpts them into the glowing apparitions that capture our imaginations, we are watching their slow disintegration, material streaming away never to be reclaimed. Even the closest passes of this seven-comet procession remain safely distant by astronomical measures. Pan-STARR's nearest approach carries it far beyond the orbit of the Moon. SWAN and the Solar Terrestrial Relations Observatory comet follow tracks that pose no conceivable risk to Earth or any other planetary body. These are encounters of spectacle, not of danger. The true sense of alarm emerges instead from human psychology. Pattern recognition, once vital for survival, urges us to seek causes when unusual events cluster. Our ancestors relied on this instinct to detect coordinated threats in natural landscapes. Today, we extend the same impulse to cosmic scales far beyond our intuition. 7 comets arrive together, and instinct whispers, who sent them? What power choreographed such precision? Why here? Why now? The questions grow sharper with the presence of 3I Atlas, an interstellar wanderer whose arrival feels uncomfortably well-timed. A narrative forms with ease. Alien probe appears. Comet swarm follows. Mystery deepens. Speculation spreads. And social media algorithms amplify the story because intrigue fuels attention, and attention fuels profit. Videos weaving hidden connections garner far more views than sober explanations of orbital mechanics. The tale grows with every retelling, fed by humanity's hunger for meaning in what so often appears to be a random universe. Here lies the responsibility of science. Bold claims must endure rigorous testing against established physics and real data. Speculation is welcome, but only when clearly marked and tethered to evidence. Beauty does not imply orchestration. Drama does not imply artifice. Magnificence does not imply menace. The cosmos routinely creates spectacles that surpass imagination without invoking exotic forces. Consider the role of solar maximum in heightening the drama of this year. Coronal mass ejections and high-speed particle streams distort cometary tails, stretching them across great arcs of the sky or tearing them in sudden disconnection events. The result can appear like coordination, as though comets brighten or shed material in unison. Images will flood online, showing what looks like synchronized dances in the heavens. The truth is subtler yet still profound. Each comet responds independently to the same solar environment, their apparent unity nothing more than weather vanes turning in the same storm. Shared exposure, not hidden command. This coincidence of cometary abundance and solar peak invites deeper questions. Why should such an unusual comet year align with the crest of solar activity? Could cycles of the Sun exert influences gravitational, electromagnetic, or otherwise that encourage comets to begin their inward journeys? These questions remain speculative, but they are tethered to measurable processes, offering fertile ground for investigation as the spectacle unfolds. Solar activity unfolds in cycles well documented across centuries, patterns that correlate with countless expressions of space weather. If solar maximum somehow increases the likelihood of comet arrivals or their detection, that connection should reveal itself within historical data spanning multiple cycles. The framework of this investigation demands constant vigilance against confirmation bias, the human tendency to read uncertain evidence as confirmation of what we already wish to believe. When we observe unusual tail behavior, the first step must be to check for solar storms, not to leap toward exotic coordination. When a comet brightens suddenly, we must examine its chemistry and the heat it absorbs from the Sun, not assume mysterious triggers. When orbital irregularities appear, we must first verify the accuracy of our measurements and account for known perturbations before invoking the influence of the unknown. This discipline does not extinguish wonder, nor does it discourage speculation. Rather, it anchors our curiosity in observation, ensuring that our sense of mystery remains tethered to evidence rather than imagination. The universe is already filled with riddles, We need not invent new ones. The convergence of 7 comets is itself a statistical rarity that demands serious attention. Such clustering happens seldom enough to justify searching for deeper causes. Should our analysis reveal nothing beyond coincidence, amplified by modern survey capabilities, that conclusion remains meaningful, adding to our grasp of solar system dynamics. But if the data expose correlations that surpass chance synchronizations of timing, alignments in orbits, or behavioral similarities that hint at shared influences, then we stand at the edge of discovery, with insights that could reshape how we understand the system we inhabit. The presence of 3I Atlas in this same remarkable year adds a dimension that turns statistical curiosity into a mystery of greater weight. Interstellar visitors enter our skies perhaps once in a decade, making their timing profoundly significant rather than incidental. We are not claiming that 3I Atlas caused or commanded the comet swarm. We are acknowledging that the coincidence warrants careful investigation rather than dismissal. Even absent direct causation, the alignment may conceal indirect relationships that help reveal hidden aspects of solar system behavior. Our accountability lies not only in avoiding false alarms, but also in refusing to overlook genuine signals in our eagerness to disprove speculation. Science has often advanced on the shoulders of ideas first dismissed as absurd, later vindicated by careful inquiry and the slow accumulation of evidence. The challenge is to maintain skepticism while staying open to truths that may challenge orthodoxy. Rigorous standards must test extraordinary claims, yet those standards must not be so rigid that they exclude extraordinary evidence when it emerges. As we prepare to meet our interstellar visitor in greater detail, let us recall that the most profound discoveries often begin with simple questions about unusual patterns. Sometimes the universe is teaching us a lesson, and sometimes that lesson arrives dressed as coincidence. The swarm has sounded its alarm, and our response must be inquiry, not panic. Whatever truth lies ahead will be revealed not by speculation, but by the careful work of measurement, analysis, and evidence. And now we turn to our prime suspect, the interstellar stranger whose arrival has cast this mystery in sharper relief. This marks the third confirmed interstellar object ever to traverse our solar system, a cosmic wanderer born around another star, now sweeping through our celestial neighborhood on a single hyperbolic passage. Unlike every comet or asteroid native to our skies, this visitor carries no local birth certificate. It is alien in the most literal sense. The weight of this distinction cannot be overstated. The 7 comets in our swarm were all forged within the Sun's gravitational domain, assembled from the same primordial materials that shaped planets and moons more than 4.5 billion years ago. By contrast, 3I Atlas brings with it ice and dust that condensed around a different star in an unfamiliar stellar nursery, under conditions beyond our direct imagining. It is as if we have discovered a message sealed in a bottle, though the bottle has not crossed an ocean, but the immeasurable gulf between stars. Its journey likely consumed millions of years, drifting in the near-perfect vacuum of interstellar space, bombarded by radiation and recording its long voyage in chemical scars. For our purposes, one fact is especially important. 3I Atlas poses no threat of collision. Its path carries it safely beyond all major planetary bodies, curving outward along a hyperbolic trajectory that will soon eject it into interstellar space once again, never to return. This is reconnaissance, not invasion if such human terms even apply to what may be nothing more than an ancient shard of frozen material wandering by chance. Yet the comet-like behavior of 3I Atlas complicates its tale. Even at great distances from the Sun, where temperatures should keep volatiles locked in solid ice, the object developed a coma and tail. By all expectations, solar heating at such ranges is insufficient to trigger visible outgassing. And yet telescopes reveal the unmistakable hazy shroud of an active comet, rather than the silence of an inert asteroid. This premature activity implies an unusual composition, perhaps containing supervolatile elements that vaporize at extremely low temperatures, or an unexpected internal heat source driving gas outward independent of solar warming. Either scenario holds tantalizing clues about the environment in which this body was formed. The excitement surrounding interstellar visitors lies in their unique status as direct samples of other planetary systems. Each measurement, spectroscopic fingerprints of chemical makeup, photometric studies of brightness variation, astrometric tracking of its exact motion delivers information about stellar formation beyond our sun's domain. But within our narrative, the more provocative question is different. Could this alien traveler be linked in some way to the remarkable timing of the 7-comet swarm? The overlap may be coincidence, but the stakes demand we examine the possibility. A true connection would appear in observable signatures, timing correlations that surpass probability, orbital relationships hinting at shared influences, behavioral anomalies better explained by interaction than by isolation. The absence of such evidence would argue against coordination, leaving us with nothing more than a fascinating alignment in the calendar of the cosmos. But the presence of genuine correlations would force us to confront questions about forces subtler and more far-reaching than the physics we know. It would suggest linkages between stellar systems transcending the simple gravity we understand today. Even without appealing to exotic mechanisms, the simultaneity of 3I Atlas and the 7-comet swarm compels attention. The universe has a way of presenting coincidences that conceal deeper truths, waiting for us to develop the instruments and the imagination to uncover them. Interstellar objects visit rarely, perhaps once in a decade according to current detection rates. Their arrivals should be scattered randomly across time, with no connection to internal solar system events. Yet here we stand, confronted by an interstellar traveler arriving during the most unusual comet year in living memory. The probability is simple to frame. If interstellar appearances and comet swarms are independent, their simultaneous occurrence should be exceedingly rare. The more unusual each individual event proves to be, the more suspicious their overlap becomes. Correlation, of course, does not equate to causation, and suspicious timing is not proof of connection, but it is justification enough for the detailed investigation we are pursuing. If the universe is whispering to us about hidden relationships between interstellar visitors and local bodies, then we must listen with sufficient care to catch the lesson. Managing expectations for 3I Atlas is essential. Unlike the potentially spectacular members of the 7-comet swarm, this visitor from afar will likely remain a telescopic object throughout its stay. Its scientific value outweighs its visual allure, for professional astronomers and skilled amateurs alike are mobilizing to maximize the knowledge gained from this brief encounter. Every photon collected from its faint glow offers irreplaceable information about the conditions in another stellar system. Its hyperbolic trajectory ensures this is a one-time meeting, never to be repeated. This campaign also offers our best chance to test whether 3I Atlas shares any connection with the 7-comet swarm. If anomalies exist, synchronized changes in brightness, correlated tail behavior, or timing relationships too precise to be random, they may reveal themselves only through careful, coordinated monitoring of all 8 objects together. Yet here lies the challenge. Human pattern recognition evolved to find meaning in noisy environments, and in our eagerness to see connection, we risk conjuring patterns from coincidence. That is why our investigation insists on strict separation between observation and interpretation. Brightness curves, orbital elements, and spectral signatures are objective measures of reality. Any effort to link those measurements into broader conclusions belongs to hypothesis testing, where skepticism must temper curiosity. The scientific method equips us for this balance. Statistical tools help determine whether observed correlations reflect chance or true relationships. Independent confirmation ensures that apparent patterns endure scrutiny across instruments and research groups. Yet even the most rigorous framework requires judgment. How much evidence is enough to support an extraordinary claim? To argue that an interstellar visitor alters cometary behavior within our solar system is an assertion of rare magnitude. Such a claim demands evidence of equal weight. As we turn to examine the orbital characteristics and predicted behavior of 3I Atlas, we must recognize what is at stake. Should genuine links between interstellar arrivals and local dynamics emerge, they would revolutionize our picture of how stellar neighborhoods interact across cosmic distances. The universe may be more tightly interconnected than present theory suggests. Its influence is subtle yet immense. Or perhaps we are simply confronting a statistical quirk, a coincidence designed to test our discipline in separating appearance from truth. Either way, the answer resides in data. The stranger has arrived, and its testimony is written in the geometry of its approach. The path of 3I Atlas reads like a cosmic passport, recording a journey that began in interstellar space and will conclude there as well. Unlike the closed ellipses that bind planets and comets into endless revolutions around the Sun, this object follows a hyperbolic course, the unmistakable signature of something moving too swiftly ever to be captured. Imagine a slingshot. It dives inward from the abyss, swings sharply around the Sun, and accelerates outward once more, vanishing into the dark without return. One passage only, no encore, and we are fortunate to witness it unfold in real time. Its orbital elements offer a story both elegant and sobering. The object approaches from a direction roughly aligned with the constellation Perseus, though interstellar space provides no clear road signs to pinpoint its place of birth. Its hyperbolic excess velocity, the speed it retains even after escaping solar gravity, implies a journey that may have stretched for hundreds of thousands of years, perhaps from neighboring stellar systems. What fascinates astronomers is not only the speed, but the angle. Rather than plunging steeply from high above or below, 3I Atlas enters at a moderate inclination relative to the ecliptic plane, the thin disk that carries planets and most native debris. This geometry ensures the object spends more time passing through the same broad region occupied by our 7-comet swarm. The distances remain vast, measured in astronomical units, far beyond the range of direct gravitational encounters. Yet its lingering presence in this shared zone commands attention, for geometry sets the stage on which subtle interactions, if any, might play out. The motion of 3I Atlas is retrograde, another detail that complicates the picture. While most solar system bodies orbit the Sun in the same direction as planetary rotation, this interstellar stranger approaches against the current. Retrograde motion generates relative velocities greater than those experienced in typical solar system encounters. Such speed minimizes gravitational influence, for the faster two objects move past one another, the less time they remain within each other's sphere of attraction. If 3I Atlas were to exert any effect on native comets, the retrograde geometry would actually hinder such influence. These orbital characteristics set clear boundaries for our inquiry. Any possible effect upon the 7-comet swarm must involve processes that do not rely on close approaches or prolonged gravitational interactions. Direct shepherding through conventional celestial mechanics grows less plausible the deeper we examine the geometry. Yet geometry alone cannot dismiss all possibilities. The timing of key orbital events may hold the crucial clues. Consider the orbital nodes, the crossing points where 3I Atlas intersects the ecliptic plane. These nodes represent moments of closest approach to the regions where native comets travel and where their debris streams lie scattered. If any interaction between interstellar and local populations exists, it is here, at these intersections, that signatures might emerge. Astronomers can calculate the precise dates of these nodal passages. Should those dates align with unexpected outbursts, unusual tail structures, or subtle orbital shifts within the 7-comet swarm, such correlations would rise above coincidence. They would become evidence, faint but real, of connection between the interstellar and the familiar. The real challenge lies in deciding what should count as unusual when comets, by their very nature, behave in unpredictable ways. Variations in brightness, shifts in tail structure, and even small orbital changes occur regularly as they respond to solar heating and the uneven thrust of outgassing. To avoid mistaking the ordinary for the extraordinary, the bar for evidence must be set high. Here, statistical analysis becomes our most reliable compass. By monitoring all 7 of the traditional comets continuously and recording every change in brightness, every alteration in tail geometry, every noteworthy fluctuation, we can test whether such events cluster disproportionately around the key orbital milestones of 3I Atlas. The null hypothesis, the default assumption that the interstellar visitor and the comet swarm are unrelated, predicts that unusual events will scatter randomly across time, showing no preference for the visitor's significant orbital dates. Any significant deviation from that random pattern would strengthen the case for connection, even if the mechanism remained unclear. Yet vigilance against selection bias is essential. It is all too easy to highlight moments that appear to support a favored conclusion while ignoring those that do not. A rigorous approach demands that we log every relevant observation, not merely the ones that suit the story. The orbital evolution of 3I Atlas itself provides fertile ground for testing. As the object approaches perihelion, solar heating should intensify, driving outgassing that may trigger brightening or fragmentation. If the 7-comet swarm responds in any correlated way, sudden outbursts or synchronized anomalies, those responses should align temporally with the interstellar visitor's predicted surges. The closer the timing match, the stronger the suggestion of connection rather than coincidence. Still, we must entertain another explanation, that any apparent correlation stems not from interaction between comets, but from shared exposure to external forces. Solar activity, fluctuations in the interplanetary magnetic field, or bursts of charged particles from coronal mass ejections can influence multiple comets at once. Such triggers could create the illusion of coordination without requiring direct communication between objects. If this solar influence hypothesis proves correct, then correlated behavior across the swarm should trace back to identifiable solar events. The orbital geometry of 3I Atlas also constrains what is possible. Its hyperbolic flight ensures only a fleeting visit, perhaps 18 months from first detection to final disappearance into interstellar night. Any influence on the 7-comet swarm must emerge quickly, during the narrow window when all can be observed with present instruments. Subtle effects building over centuries lie beyond the reach of this encounter. And so we arrive at perihelion, the critical moment for every comet. Here, the slow approach accelerates into a fiery crescendo as icy reserves boil away under the sun's full radiance. For 3I Atlas, this passage carries particular weight. It will be the point at which an interstellar traveler feels the complete force of our star, a crucible in which its behavior may either confirm the expectations of physics or hint at deeper mysteries. Orbital mechanics dictates the timing with absolute precision, indifferent to human speculation. The numbers will not lie. Whether those numbers reveal connections to the 7-comet swarm is the question perihelion may finally answer. The physics of perihelion are as inevitable as they are dramatic. As 3I Atlas draws nearer to the sun, the power of solar radiation increases with ruthless precision, following the inverse square law. Halve the distance, and the heat and brightness quadruple. Ice that survived for millions of years in the deep freeze of interstellar space begins to vaporize, wrapping the once dark shard in a luminous veil of gas and dust. It is this transformation from silent stone to glowing apparition that turns an interstellar wanderer into a comet. Yet the ice of 3I Atlas is not expected to match that of familiar solar system comets. Formed in the outer reaches of another stellar nursery, it may carry molecules uncommon in our neighborhood. Carbon monoxide, carbon dioxide, methane, or even more exotic compounds could dominate its interior. Each of these substances leaves behind a distinct spectroscopic signature when vaporized by sunlight. During perihelion, the spectrum of 3I Atlas will function like a chemical fingerprint, an unbroken record of its birthplace preserved across a voyage that may have lasted millions of years. If there are genuine links between 3I Atlas and the 7-comet swarm, perihelion is the moment when such connections are most likely to reveal themselves. The intense heat of the sun drives comets to their peak activity, and in this crucible even subtle coordination mechanisms might become visible. Astronomers will be watching for sudden changes, outbursts in brightness, jets of material, or unexpected tail behavior. A single outburst can amplify a comet's brightness by a factor of 10 or more in a matter of hours, as volatile substances erupt or as protective crusts erode to expose fresh ice. Such flashes provide extraordinary opportunities for observation, while also offering clues to internal structure and composition. Jets erupting from specific points on the nucleus can impart asymmetric thrust, nudging the orbit slightly. These non-gravitational forces are well documented among solar system comets, but observing them in an interstellar body would offer unparalleled insight into how foreign materials respond to our sun's influence. The evolution of the tail system will be especially revealing. Ion tails, created when ultraviolet sunlight ionizes gases, stream outward under the push of the solar wind and the sun's magnetic field. Their length, shape, and reaction to changing solar conditions will show us how matter from another star system interacts with ours. Dust tails, by contrast, are sculpted by radiation pressure. Coarser grains resist deflection, while fine particles bend into elegant arcs that may span vast swaths of sky. An unusually brilliant dust tail could suggest a nucleus rich in delicate grains, easily swayed by sunlight, or it might result from sudden fragmentation that releases reservoirs of hidden material. Fragmentation itself represents the most dramatic possibility. As solar heating, rotational stress, and internal pressure from volatile gases combine, a comet's fragile cohesion can fail. When that happens, it breaks apart, sometimes into multiple pieces strung along the orbit like beads. For 3I Atlas, such an event would carry extraordinary significance. Shattered fragments would expose untouched interiors, materials unaltered since the dawn of its formation in a foreign stellar system. For scientists, it would be nothing less than a once-in-a-lifetime opportunity to read the innermost secrets of an alien worldlet, laid bare under the gaze of our star. The fresh surfaces revealed by a breakup would open extraordinary opportunities for spectroscopic study, exposing pristine interstellar material untouched since its birth in a distant stellar nursery. Yet fragmentation could also complicate our investigation into possible links with the 7-comet swarm. Multiple fragments, each following slightly diverging paths, might give the illusion of coordinated behavior, where none truly exists, an artifact of geometric complexity as astronomers attempt to track several related objects at once. The solar wind environment during the perihelion passage of 3I Atlas introduces yet another variable. Under solar maximum conditions, particle densities rise, magnetic fields strengthen, and coronal mass ejections erupt more frequently. These forces can transform comet tails into spectacular displays. Sudden disconnections, plasma instabilities, and magnetic reconnections that twist or sever tails entirely. Such effects occur independently within each comet's environment, but because they respond to the same solar triggers, they can produce the appearance of synchrony across multiple objects. Distinguishing genuine coordination from shared responses to solar weather requires precision in both timing and geometry. Disturbances in the solar wind travel outward at predictable velocities, reaching different comet positions at calculable intervals. If anomalies in the 7-comet swarm align with events in 3I Atlas but cannot be explained by those propagation delays, then the correlation becomes far more compelling. To capture such details, armies of eyes will be watching. Amateur astronomers worldwide are preparing campaigns to monitor 3I Atlas during its close approach, forming a network of citizen scientists whose distributed coverage can achieve what no single observatory could. Continuous light curves, photographic records of tail development, and real-time alerts of sudden outbursts or possible fragmentation will flow from backyards and small telescopes across the globe. Professional facilities will add their weight, from ground-based observatories to space-based telescopes and dedicated comet survey systems, converging in what may become the most comprehensive study of an interstellar visitor ever attempted. Every photon collected will carry irreplaceable data, a fragment of knowledge about conditions beyond our Sunday. But to test for correlations, we must also observe the 7 traditional comets alongside the interstellar stranger. Only by cataloging their behavior during the same period, tracking brightness variations, tail anomalies, or orbital shifts, can we determine whether apparent links surpass statistical chance. The precision demanded by this task stretches current capabilities to their limits. Subtle brightening, faint asymmetries in tails, or minute orbital perturbations may be the only evidence available, signs of interactions operating below the threshold of conventional detection. As perihelion draws near, we must remember a simple truth. The universe obeys its laws without regard for human expectations. 3. Atlas will brighten, sprout tails, and perhaps fragment, all according to its internal chemistry and the inexorable heat of the Sunday. It carries no hidden purpose, no script written to astonish us. And yet, within these natural processes lie opportunities for profound revelation. Whether those revelations include a connection to the 7 comet swarm remains uncertain. What is certain is that careful observation, not speculation, will decide the answer. The cosmic clockwork will continue to turn with perfect precision, indifferent to our hopes, but faithful in providing the data from which truth can be drawn. Our sun operates on cycles so vast that they dwarf human attention spans, alternating between calm interludes and violent outbursts with the steady beat of a cosmic metronome. The 11-year solar cycle that governs this rhythm is now climbing to its peak in the year 2025, turning our star into a more turbulent and more visually spectacular version of itself. At solar maximum, the sun becomes mottled with sunspots, dark blemishes where magnetic fields pierce its surface and store immense reservoirs of energy. When that energy breaks free, it does so explosively, flinging charged particles and electromagnetic radiation outward at velocities that sweep across the solar system in mere hours or days. For our investigation into the 7 comet swarm, this enhanced solar activity is both a gift and a complication. The denser particle streams and stronger magnetic fields of solar maximum can exaggerate comet tail behavior, making modest objects look far more dramatic than they would during quieter times. Imagine a coronal mass ejection, a billion-ton bubble of magnetized plasma hurled into space. When it collides with the fragile ion tail of a comet, the results can be breathtaking. Shockwaves and magnetic distortions twist, compress, or even sever the tail completely in a matter of hours, creating some of the most extraordinary comet images ever captured. Such tail disconnection events occur when the magnetic polarity of the solar wind flips too abruptly for a comet's existing tail to adjust. The old tail is abandoned, drifting away as a ghostly ribbon of debris, while a new one begins to grow in alignment with the altered magnetic field. To the untrained eye, these transformations can seem supernatural. Tails sprout kinks, knots, and spirals that appear to defy the simple physics of gas streaming from ice. Sometimes the tail appears to vanish entirely, leaving the eerie impression that the comet has been struck or wounded. In truth, the comet itself remains intact. Only its luminous veil of ionized gas reshapes itself in obedience to the shifting solar wind. This solar influence matters greatly to our study, because all 8 objects under our scrutiny, the 7 traditional comets, and the interstellar traveler, 3, Atlas, share the same space weather environment. Each one will endure the same solar storms, the same particle streams, the same magnetic fluctuations. If dramatic changes appear across multiple comets at the same time, the simplest explanation is that they are all responding to the same solar trigger. A single massive storm can ripple through the inner solar system, producing synchronized effects that mimic coordination without requiring any actual connection between comets. The heightened activity of 2025 does not stop at comet tails. Earth itself feels the consequences. Geomagnetic storms sparked by solar particles buffet our magnetosphere, sometimes disrupting satellites, interfering with navigation systems, and even threatening power grids. At the same time, auroras bloom at latitudes far below their usual polar haunts, painting skies above temperate regions with curtains of green and crimson. The spectacle of radiant comets sharing the sky with auroras creates a tableau so astonishing that it invites myths of cosmic conspiracy. Yet it is crucial to remember that the sun drives both phenomena independently. Comets do not disturb Earth's magnetic field, nor do auroras arise from interstellar visitors. They are parallel consequences of solar activity, not evidence of hidden causality. Still, the timing of solar maximum relative to this unprecedented comet year sparks provocative questions. Could heightened solar activity influence how often comets are nudged inward from the outer solar system? Might electromagnetic or gravitational effects associated with solar storms subtly shape the timing of arrivals? These questions belong to the realm of speculation, but they remain grounded in phenomena that can be measured, modeled, and tested. Solar activity unfolds in cycles so well documented that any true correlation with comet behavior should leave detectable traces in the statistical record. Historical data stretching across multiple solar cycles provides the foundation for such an inquiry. If active solar phases regularly align with increased comet activity, the pattern should appear in that archive more often than chance alone would predict. The task is to test whether the spectacular clustering of comets in the year 2025 represents a natural alignment with solar maximum, or whether something beyond conventional space weather is at work. The separation of solar effects from possible links between 3I Atlas and the 7-comet swarm is central to the investigation. When a comet's tail suddenly twists, disconnects, or brightens, the first response must always be to consult space weather reports. Coronal mass ejections, high-speed solar wind streams, or magnetic disturbances frequently create precisely those phenomena. Only after eliminating known solar causes should we consider more exotic explanations. This disciplined approach safeguards us from premature conclusions and protects against the temptation to elevate coincidence into conspiracy. Professional monitoring infrastructure makes this discipline possible. The Solar and Heliospheric Observatory, the Solar Dynamics Observatory, and worldwide magnetometer networks maintain continuous surveillance of solar activity, mapping both immediate conditions and their propagation through interplanetary space. These instruments provide a near real-time account of the sun's changing moods. They give astronomers the ability to match cometary events with specific solar triggers, distinguishing normal responses to solar weather from truly anomalous behavior that may hint at deeper forces. If 3I Atlas exerts any influence on traditional comets, its signature must rise above this solar background. That influence must reveal itself as correlations that cannot be explained by known solar variability. Here, amateur astronomers play a vital role. With cameras and telescopes scattered across the globe, they record brightness fluctuations, tail structures, and outbursts with a frequency that often surpasses the schedules of professional observatories. Their collective vigilance creates a continuous, distributed dataset covering every member of our comet cast. The richness of this record strengthens our ability to perform correlation analysis, identifying events that deserve further scrutiny. The elevated solar activity of 2025 ensures a complex backdrop for this study. Comets will be bathed in dense particle flows and turbulent magnetic fields. Tails will twist, sever, and regrow in spectacular displays that make for unforgettable photographs, but complicate the search for subtler, non-solar influences. The challenge is to hold the evidentiary bar high, to remain open to discovery without succumbing to wishful interpretation. The history of astronomy is filled with moments when unexpected connections emerged only because careful observers refused to dismiss anomalies too quickly. Solar maximum may offer the very conditions necessary for detecting faint interaction effects that would otherwise remain invisible. As the investigation broadens to include how solar weather shapes Earth's own environment, one truth remains clear. The Sun is the principal architect of comet behavior, its magnetic fields and particle streams weaving a choreography that binds our star to every icy traveler within its gravitational reach. Yet within this familiar rhythm, New steps may be waiting, subtle patterns that reveal themselves only when the universe decides to lift the veil. The influence of space weather on Earth reveals a lattice of vulnerabilities hidden beneath the surface of daily life, rarely noticed until systems falter without warning. Comets themselves pose no direct risk to our planet, yet the same solar activity that makes their tails shimmer with ethereal beauty can wreak havoc on the technological backbone of modern civilization. Geomagnetic storms, Earth's response to surges of solar particles, induce powerful electrical currents in long-distance transmission lines. These currents can overload transformers, melt conductors, and trigger cascading failures that leave entire regions in darkness. The storm of March in the year 1989 provided a vivid demonstration when Quebec's electrical grid collapsed in less than 2 minutes, plunging millions of people into a sudden blackout caused not by earthly weather, but by disturbances launched from the Sunday. Satellites, orbiting far above the relative safety of Earth's atmosphere, face even more direct exposure to solar particle bombardment. High-energy protons and electrons accelerated by solar storms pierce spacecraft shielding, disrupt circuits, and sometimes destroy delicate electronics permanently. Navigation networks that depend on the global positioning system, communication relays that link continents, and even weather satellites designed to monitor storms below all grow unreliable during solar outbursts. Temporary malfunctions may pass unnoticed, but severe storms can create widespread disruptions with consequences reaching deep into terrestrial life. Aviation adds another layer of concern. Over polar routes, where Earth's magnetic field offers less protection against cosmic radiation, aircraft encounter heightened risks during geomagnetic storms. Airlines often reroute flights away from high latitudes during severe events, protecting not only passengers and crew from increased radiation exposure, but also shielding sensitive avionics systems from interference. These diversions are costly, but they underscore how profoundly space weather shapes human activity, even in realms far removed from astronomy. Such vulnerabilities create fertile psychological ground for misinterpretation. When comet activity peaks in the same year as solar maximum, the timing appears uncanny. Power outages, communication breakdowns, and navigation errors feel like evidence of exotic influences from the unusual 7-comet swarm. Yet the truth is far more grounded, though no less fascinating. Solar storms affect both comets and Earth's infrastructure, but through entirely separate mechanisms. Comets respond in space to changes in particle density and magnetic turbulence, while Earth suffers impacts when those same particles interact with its magnetosphere. The parallel timing arises from a shared solar cause, not from any mysterious influence exerted by comets themselves. This distinction becomes even more vital when the interstellar visitor, 3I Atlas, enters the conversation. Should satellites fail or power grids falter during its passage, the explanation lies not in the feeble gravity of a small distant body, but in the immense energy of solar storms. The temptation to weave a narrative of cosmic causation must give way to the discipline of physics. Established mechanisms, not speculative connections, provide the most reliable guide. Fortunately, government agencies have developed sophisticated systems to monitor and forecast space weather with the same urgency applied to hurricanes or tornadoes. The Space Weather Prediction Center of the National Oceanic and Atmospheric Administration issues alerts tracking solar flares from their fiery birth on the Sun to their impact on Earth's magnetic shield. These forecasts allow operators to prepare for disruptions and provide a framework for correlating infrastructure failures with documented solar events. If problems coincide with periods of geomagnetic unrest, solar activity becomes the overwhelmingly likely cause rather than the passing of comets. Amateur observers also contribute to this vigilance. Radio enthusiasts notice disruptions in ionospheric transmission long before official bulletins are issued. During geomagnetic storms, familiar frequencies vanish into static, while signals bounce unexpectedly across continents. These grassroots observations provide real-time confirmation of solar activity, extending the sensory network that helps scientists and the public alike distinguish between solar-driven effects and anomalies that might warrant deeper study. The solar maximum of 2025 will guarantee frequent opportunities for such correlations. Several geomagnetic storms each month will offer chance alignments between comet appearances and terrestrial disruptions. Statistical probability ensures that coincidences will occur, but careful observation and disciplined analysis will reveal the true source. The sun, not comets, drives the storms that test our fragile technologies. Within this recognition lies not disappointment but wonder, that distant eruptions on a star 93 million miles away can shape the flicker of lights in our homes and the hum of circuits in our machines. If 3I Atlas exerts any influence upon Earth's electromagnetic environment, those effects should be measurable through numerous independent monitoring systems. Yet the framework of investigation must be guided by vigilance, for the human mind is prone to error when dramatic events overlap in time. Psychology favors causality over coincidence. When the timing of two unusual events coincides, the instinctive conclusion is that one must have caused the other. The rarer the events, the more irresistible their apparent connection becomes. But probability teaches a harsher lesson. Improbable clusters appear regularly in random distributions. Flip a coin for long enough, and runs of 10 heads in a row will eventually emerge, no matter how astonishing they seem. The same truth applies to overlaps between solar storms, cometary displays, and failures of technological systems. The challenge lies in crafting objective criteria that separate genuine correlation from the kind of clustering that naturally emerges from complexity. This requires first establishing a baseline. How often should comet outbursts, space weather disturbances, and infrastructure problems coincide purely by chance? Only against this statistical background can we test whether observed overlaps carry significance or whether they are illusions conjured by probability. Professional space weather research has developed tools suited to this very task. Techniques such as superposed epoch analysis, cross-correlation functions, and other statistical frameworks allow researchers to measure the strength of relationships between datasets while compensating for the multiple comparisons problem that trap where testing many possible correlations guarantees that some will appear significant simply by accident. Applied rigorously, these methods create a shield against the pattern-seeking biases that so easily seduce human perception. They ensure that claims linking 3I Atlas to terrestrial effects rest on measurable evidence rather than narrative appeal. The standard of proof must remain appropriately high. Lower the bar, and false alarms multiply, eroding confidence in genuine discoveries. Raise it too far, and subtle but real signals may be missed. The art of investigation is to balance sensitivity with skepticism. Modern technological civilization, sprawling and interconnected, generates fertile ground for coincidence. Millions of satellites, billions of devices, and countless transmission networks hum ceaselessly, and failures occur daily for mundane reasons. During quiet periods, these disruptions are attributed to aging equipment, software errors, or simple wear and tear. Yet when a blackout, a navigation glitch, or a communication outage unfolds amid heightened astronomical interest, suspicion takes root. What might once have been blamed on corroded cables is suddenly linked to comets streaking across the sky. Education becomes the antidote. The more widely the public understands the actual mechanisms by which solar storms disturb magnetospheres, satellites, and grids, the less room exists for speculation that interstellar wanderers are pulling unseen strings. Clear communication ensures that exotic hypotheses can be explored without being mistaken for established truth. The line between evidence and speculation must remain bright. The rise of modern monitoring systems amplifies both opportunity and risk. Instruments today are sensitive enough to detect electromagnetic fluctuations that earlier generations could never measure. This heightened awareness may one day uncover subtle interactions, but it also multiplies the risk of false positives. In a world where every flicker of the grid or hiccup of a satellite is instantly logged, the temptation to connect dots grows stronger. More data offers more chances to mistake noise for signal. As we prepare to examine how psychology and culture shape our interpretations of celestial events, one truth remains constant. The universe operates according to physical laws indifferent to our hunger for mystery. Earth's response to solar storms follows established mechanisms: magnetic reconnections, induced currents, charged particle showers. These processes neither require nor invite exotic explanations. Even in a year crowded with comets, the reverberations that ripple through our infrastructure come from the sun, not from icy fragments wandering nearby. Yet within the steady rhythm of known physics, faint signals may still wait. Instruments may one day capture patterns that push beyond coincidence into causation, revealing influences too subtle for past generations to detect. Until then, our investigation continues firmly grounded in science, cautious before coincidence, but alert to the possibility that even familiar laws may yet hold unimagined complexities linking the heavens to the world below. Throughout human history, the sudden brilliance of comets has been received not simply as astronomical phenomena, but as messages written across the heavens. Civilizations saw in them reflections of their deepest fears, their highest hopes, and their most pressing uncertainties. The simultaneous appearance of multiple comets, as in the year 2025, activates psychological patterns as old as humanity itself, transforming objective celestial mechanics into narratives about destiny, upheaval, and cosmic intent. Ancient Chinese astronomers, perhaps the most meticulous chroniclers of celestial events, recorded comet appearances with precision and seriousness. In the dynastic annals of the Han, comets were described as broom stars, sweeping away the remnants of the old order to prepare space for renewal. This metaphor of cleansing reveals a culture deeply invested in cosmic timing, interpreting each bright visitor as a harbinger of political change or natural upheaval. In medieval Europe, comets carried similar weight, but were framed through the lens of Christian cosmology. Chroniclers described them as divine warnings, celestial signals of wars, plagues, or the deaths of kings. The Great Comet of the year 1066 became forever associated with the Norman invasion of England. Whether the comet shaped events or simply provided convenient symbolism remains unknowable, but the association endures in tapestry, chronicle, and collective memory. By the 18th century, as Newtonian physics gained authority, comets carried both scientific and symbolic weight. The return of Halley's Comet in the year 1758 coincided with the 7 Years' War, a conflict that transformed political boundaries across 3 continents. In colonial America, observers interpreted the comet as an omen of independence from British control, while in Europe, astronomers celebrated it as triumphal proof of universal gravitation. The same event supported divergent narratives, shaped not by celestial truth, but by human context and political aspiration. These episodes illustrate a timeless pattern. When unusual phenomena cluster, human minds weave them into coherent stories. Wars, famines, plagues, and comets rarely arrive on coordinated schedules. Yet when they do overlap, coincidence feels inadequate. Populations, particularly during times of uncertainty, crave signs that the cosmos itself is speaking. The year 2025 arrives against a backdrop of climate anxiety, technological disruption, and geopolitical tension. The stage is set for the 7-comet swarm to be read not as chance, but as prophecy. In earlier centuries, the narratives would have been preserved in illuminated manuscripts, chronicles, or oral tradition. Today, the mechanism is faster, louder, and far more pervasive. Social media algorithms amplify dramatic images and speculative theories, favoring engagement over accuracy. Videos of luminous comet tails streaking across skies, overlaid with ominous music and confident narration, spread faster than measured explanations of orbital mechanics. The psychological wiring that once helped humans detect genuine patterns in nature is now hijacked by platforms designed to maximize attention. This democratization of content creation means that narratives arise in parallel across the globe. A teenager in Brazil, a filmmaker in Poland, and a conspiracy theorist in California may all independently create comet videos suggesting cosmic meaning. Their convergence, algorithmically amplified, creates the illusion of consensus, even when their claims lack factual grounding. Each retelling adds details: alien probes, hidden warnings, cosmic cycles, until the original fact, 7 comets arriving in a single year, becomes nearly unrecognizable. The presence of 3I Atlas in this crowded narrative landscape provides irresistible material. An interstellar visitor, arriving during the busiest comet year in recent memory, invites purposeful interpretation. The storyline writes itself: a probe from beyond coordinates with a comet swarm to deliver a message to Earth. Such narratives satisfy multiple psychological needs at once. They provide explanation for timing, assign agency to randomness, and elevate human observers into participants in a cosmic drama. Professional astronomy struggles to compete with these stories. Statistical models, careful caveats, and orbital charts rarely inspire the same emotional engagement as a cinematic video proclaiming cosmic warning. Scientists, bound to honesty about uncertainty, often sound less convincing than content creators who confidently assert hidden meaning. Yet the responsibility remains clear: to present evidence with integrity, neither inflating speculation into fact nor dismissing anomalies without due attention. The comet swarm of 2025 will test this balance. Humanity will once again project meaning onto the sky, as it always has. But the task of science is to illuminate truth within the spectacle, to separate celestial choreography from the narratives we weave around it, and to remind us that wonder need not depend on mystery alone. When we acknowledge that some correlations rise above what statistics would predict, while simultaneously reminding audiences that correlation is not causation, we run a risk. The caution that defines science can sound less compelling than the confidence of sources offering definitive answers, even when those answers lack foundation. Yet this very tension also creates an opportunity. The extraordinary attention focused on the 7 comet investigation opens a rare window for teaching the public about hypothesis testing, probability, and the essential difference between evidence and interpretation. Transparent separation of established facts from speculative possibilities allows science communicators to model the process of inquiry itself, showing how extraordinary claims demand extraordinary evidence, while also demonstrating that unusual observations deserve careful examination rather than dismissal. The cultural lens through which individuals interpret our findings inevitably shapes the conclusions they draw. Those inclined toward belief in extraterrestrial visitation will interpret any ambiguous result as validation of their conviction. Skeptics committed to conventional explanations will dismiss even compelling correlations as insufficient to justify revision of established theory. This polarization reflects a deeper philosophical divide. How do we decide what counts as reliable knowledge, and what standard of evidence must be met before extraordinary claims are entertained? Different communities answer these questions differently, shaped by education, worldview, and personal history. The scientific method insists on provisional acceptance, embracing conclusions only as strongly as the evidence permits and revising them when new data emerges. This intellectual humility can appear uncertain compared to the bold declarations of both true believers and committed skeptics. Yet such flexibility represents science's greatest strength. It is precisely this willingness to adjust to new information that separates discovery from dogma, truth from comforting narrative. The history of astronomy is filled with lessons in this balance. Ideas once dismissed as absurd: the motion of Earth itself, the existence of other galaxies, the expansion of the universe, eventually proved correct through mounting evidence. Conversely, elegant theories, passionately defended, have collapsed when confronted with more precise data. Our investigation into potential links between 3I Atlas and the 7 Comet swarm must navigate these cross-currents with discipline. The evidence must speak in its own voice, without being drowned out by cultural anxieties or captured by sensational storytelling. Maintaining rigorous standards for interpretation does not mean closing our eyes to anomalies. It means remaining open to signals that may stretch conventional assumptions while demanding that such signals survive the scrutiny of measurement, analysis, and independent confirmation. As we turn toward the more sensational interpretations circulating in the public imagination, we must remember that fascination with cosmic mystery is not folly, but a profound expression of wonder. For millennia, humans have read the heavens as texts written for them, interpreting comets as omens of war, plague, or renewal. In their intuition lies a kernel of truth. Celestial events do carry messages, but those messages are written in the languages of orbital mechanics, spectroscopy, and physics, not in prophecy or magic. The harbingers have indeed arrived, their tails writing luminous arcs across the sky. They carry messages not of doom, but of data information about the chemistry of distant worlds and the dynamics of interstellar journeys. Our task is to decode these messages faithfully, while also decoding the colorful human stories that inevitably gather around such rare alignments in the sky. The most sensational interpretation of our 7 Comet swarm demands courage to articulate clearly. It is the hypothesis that 3I Atlas is not a natural body at all, but rather an artificial probe dispatched from another civilization, and that the 7 traditional comets represent a coordinated fleet responding in formation to its arrival. This line of thought pushes us well beyond the boundaries of conventional astronomy into speculative territory. It requires extraordinary evidence to be taken seriously, yet the implications are so profound that outright dismissal without examination would be just as unscientific. To assess such a claim properly, we must consider what genuine artificial origin would look like when examined through the lens of physics, not fantasy. An engineered object traveling between stellar systems would face technological challenges that dwarf human capabilities. Propulsion across interstellar distances requires staggering amounts of energy. Accelerating even a small probe to the velocities necessary for practical interstellar travel would demand power sources that eclipse everything humanity currently controls. Concepts such as nuclear pulse propulsion, antimatter engines, or still undiscovered physics would be required to achieve the speeds that bring objects across light years of space in less than geological timescales. Navigation is equally daunting. The trajectory of 3I Atlas demonstrates remarkable precision in its targeting of our solar system from potential launch points hundreds of light years away. Such accuracy would require exquisite knowledge of stellar positions, their motions over millions of years, and computational models of astonishing scope and power. While these engineering challenges are immense, they do not violate the known laws of physics. It is conceivable that advanced civilizations could, over long spans of time, solve these problems through mastery of principles we already understand, though cannot yet implement. Thus, the critical question is not whether such probes are theoretically possible, but whether 3I Atlas exhibits characteristics that distinguish artificial construction from natural origin. Spectroscopic analysis offers our most direct test. Natural comets display familiar emission lines: water vapor, carbon monoxide, carbon dioxide, simple hydrocarbons, molecules formed easily in the frozen outskirts of stellar nurseries. An artificial probe might contain refined metals, exotic alloys, synthetic compounds, or other manufactured substances absent from comet-forming environments. If the spectrum of 3I Atlas reveals such anomalies, it would provide strong evidence of engineering. Conversely, a spectrum entirely consistent with natural cometary chemistry would argue powerfully against artificial origin. Behavioral analysis provides a second line of evidence. Natural comets obey the dictates of gravity, their paths occasionally perturbed by jets of gas venting from sun-warmed ice. By contrast, artificial probes might display deliberate course corrections, rotational adjustments, or unexpected changes in trajectory. So far, the orbital elements of 3I Atlas appear consistent with a natural object. The slight deviations observed are well explained by outgassing. There is no sign of controlled maneuvers. Still, subtle corrections designed to mimic natural behavior could remain below our present thresholds of detection. Communication signatures form the third and perhaps most decisive test. An operating probe would likely maintain some form of contact with its makers, perhaps through radio waves, laser pulses, or exotic methods beyond our imagination. The search for extraterrestrial intelligence community has well-established protocols for scanning suspected targets across multiple frequencies, distinguishing artificial signals from natural cosmic noise. Thus far, systematic monitoring of 3I Atlas has revealed no transmissions. Silence, however, is not conclusive. Advanced civilizations might employ communication technologies we neither recognize nor monitor. The coordination hypothesis extends the artificial origin scenario even further, suggesting that the 7 traditional comets are themselves components of an engineered fleet, timed to arrive in response to the interstellar visitor. This extraordinary claim requires assumptions of unimaginable sophistication. Civilizations capable not merely of sending a single probe across interstellar space, but of orchestrating the trajectories of 7 separate comet-like bodies across millions of years, ensuring their simultaneous arrival with precision that transcends coincidence. No current evidence supports such a staggering proposition, yet the mere fact that it can be articulated demonstrates how profoundly the unusual timing of 3I, Atlas, and the 7 comet swarm challenges human imagination. The burden of proof remains enormous, but the investigation is worthwhile, if only to remind us of the boundary between natural wonder and the realm of the possible. Each member of our comet swarm would require independent propulsion and navigation systems sophisticated enough to coordinate arrivals within narrow time windows. The logistics of such coordination stretch beyond the limits of human imagination. 7 distinct objects, launched from potentially different locations at different times, all converging within months of each other, after journeys lasting thousands or even millions of years. This is a scenario worthy of science fiction rather than observational astronomy. Yet when we examine the evidence, the orbital characteristics of our 7 traditional comets bear the unmistakable fingerprints of solar system origin. Their compositions align with the expected chemistry of bodies formed in the icy reservoirs of the outer system. Their discovery histories trace back to survey programs that have documented their positions and motions for years, sometimes decades, with no gaps or mysteries in their records. Their trajectories display no evidence of course corrections, no signs of artificial maneuvers, and no anomalies that resist explanation within the framework of known gravitational dynamics. If these objects were artificial constructs, then they would represent one of the most sophisticated camouflage operations imaginable, perfectly designed to mimic every detail of natural comet behavior. Such deception would require intimate knowledge of human astronomical capabilities, including the sensitivity of our telescopes, the algorithms of our detection software, and the thresholds we use to classify objects as natural. It would suggest surveillance and analysis capacities far greater than the technologies such objects appear to display. The paradox is unavoidable. To appear so ordinary, they would need to be extraordinarily advanced. The timing correlation between 3I Atlas and the 7 comet swarm remains the strongest argument for considering coordination. The fact that our 3rd confirmed interstellar visitor arrives in the same year as the most unusual concentration of comets in recent memory raises eyebrows even among cautious astronomers. Statistical analysis of comet arrival patterns may reveal that the year 2025 represents an outlier, a clustering that exceeds reasonable expectations for random distribution. Yet timing alone cannot bear the weight of extraordinary claims. Against the backdrop of modern survey technology, which finds more objects every year, and the natural variability in comet discovery, coincidence remains the more plausible explanation. The appeal of alien hypotheses reveals more about human psychology than astrophysics. Faced with unusual coincidences, we naturally prefer explanations that invoke agency. Purpose feels more satisfying than randomness. The suggestion of intelligent design behind celestial patterns resonates with deep-seated needs for meaning, reassurance, or narrative clarity. In an age of technological anxiety and existential uncertainty, the thought of advanced civilizations visiting our solar system provides both comfort and excitement. It reassures us that we are not alone, while also offering a vision of technological achievement beyond our present limitations. But extraordinary claims require extraordinary evidence. The assertion that 3I Atlas or any of the 7 comets are artificial constructs falls squarely into this category. The burden of proof lies not on skeptics to disprove exotic possibilities, but on proponents to present evidence that survives the most rigorous scrutiny. At present, observational data offers no such proof. Spectra match natural cometary compositions, orbits follow gravitational predictions, light curves behave as expected for icy bodies responding to solar heating. We cannot entirely rule out the possibility of camouflage, of advanced probes designed to mimic comets so perfectly that they evade detection as artificial. Yet such scenarios require assumptions about alien capabilities and intentions that extend far beyond what the data suggests. The more assumptions we must add to keep a hypothesis alive, the weaker it becomes as a scientific explanation. The investigation continues, as closer approaches allow more detailed spectroscopic studies and higher resolution imaging. Each additional observation tightens the constraints, reducing the range of plausible exotic interpretations while increasing confidence in conventional ones. If genuine anomalies emerge, materials unknown in natural contexts, maneuvers inconsistent with physics, or unmistakable signals of communication, then the conversation will change dramatically. Until then, scientific humility demands that we treat the alien hypothesis as speculation, not conclusion. This position does not diminish wonder. On the contrary, it preserves the balance between curiosity and caution. The history of science shows us that the universe occasionally delivers phenomena that overturn expectations, but also that most apparent anomalies resolve into ordinary processes once sufficient data is gathered. The arrival of 3I Atlas and the unusual comet year of 2025 challenge us to hold both possibilities in mind. The universe may be surprising us with subtle lessons, or it may simply be reminding us of the power of coincidence. As human imagination races ahead, darker narratives take form. Some interpretations frame the convergence of comets as a harbinger of catastrophe, transforming ice and rock into cosmic weapons directed against Earth. In this telling, the year 2025 becomes the stage for civilization-threatening impacts, orchestrated by forces beyond human control. Such doomsday scenarios make compelling stories for fiction, but responsible investigation requires sober assessment of actual risks. Real impact hazards follow clear and calculable physics. Astronomers track near-Earth objects continuously, computing orbital intersections and predicting probabilities of collision with mathematical precision. When a genuine threat emerges, it can be measured, quantified, and, in some cases, mitigated. The terror belongs to the stories, not to the skies. The orbital mechanics that guide celestial bodies function with the precision of a master clockmaker, leaving no room for ambiguity when calculating genuine collision risks. None of the 7 members of our comet cast pan-stars: Swan, Stereo, Atlas K1, Atlas G3, Lemon, and Neat follows a trajectory that poses any danger of impact with Earth during their current approaches. Their closest passes remain measured in millions of kilometers, far beyond the gravitational influence zones that could redirect them onto catastrophic paths. 3I Atlas, the interstellar wanderer, moves along a hyperbolic trajectory that ensures its safe passage past every major solar system body. In fact, its foreign origin and extraordinary velocity relative to native solar system objects reduce, rather than increase, the possibility of collision. Gravitational capture becomes impossible for an object traveling at hyperbolic speeds, guaranteeing that this visitor will enter and exit our neighborhood without the faintest chance of striking our planet. The absence of direct impact risk does not eliminate every potential hazard associated with heightened comet activity. The year 2025 coincides with solar maximum, the most turbulent phase of the Sun's 11-year magnetic cycle. During this period, intensified solar storms can unleash vast streams of charged particles, bombarding the solar system with energetic radiation. These space weather effects pose significant risks to human technological infrastructure. Electrical power grids face the danger of induced currents that can overload transformers. Satellites may experience malfunctions as high-energy particles penetrate delicate circuitry. Navigation networks such as global positioning systems become unreliable under geomagnetic stress, while radio communications suffer blackouts or distortions. Yet these vulnerabilities stem directly from solar behavior, not from the comets themselves. The timing correlation between active comets and active solar conditions reflects the fact that both are subject to the same overarching rhythms of the solar system, not because comets exert any influence on the Sun's activity. Quantifying risk requires careful statistical separation of genuine threats from apparent patterns that merely appeal to human intuition. Our brains evolved to detect connections, even in random events, because in ancestral environments, the cost of missing a real pattern could mean death. But this survival strategy leads us to overestimate threats when multiple low-probability events occur together. Professional risk analysis employs mathematical frameworks that account for these tendencies, particularly the problem of multiple comparisons. When many potential relationships are tested simultaneously, some apparent patterns will inevitably emerge purely by chance. Without rigorous statistical correction, these coincidences appear more meaningful than they truly are. The doomsday scenario that gains traction in the popular imagination arises from bundling our 7 comets and 3-eye atlas into a single narrative of threat. By treating them as one orchestrated entity, human perception transforms 7 independent low-risk events into an apparently unified high-risk crisis demanding attention. But celestial mechanics recognizes no such bundling. Each object moves along its own trajectory, governed by gravity and its initial conditions, entirely indifferent to the presence or timing of the others. What appears coordinated in our perception is, in reality, an artifact of observation, timing rather than interaction. History offers valuable perspective. Across millennia, bright comets have coincided with wars, plagues, famines, and political upheavals. Ancient chroniclers repeatedly connected these celestial appearances with terrestrial suffering. Yet, systematic analysis reveals no statistical correlation between comet apparitions and increased rates of disaster. The illusion of correlation arises because unusual celestial events attract heightened notice during times of crisis. When societies are already struggling, chroniclers seize upon any dramatic sign in the heavens as a portent. In contrast, identical astronomical events that occur during peaceful years often fade quickly from memory. Modern civilization faces no shortage of real existential threats. Nuclear weapons, climate change, global pandemics, and technological disruptions pose dangers that can be modeled, measured, and mitigated through deliberate action. These are challenges rooted in established science and observable mechanisms. The apocalyptic comet narrative, in contrast, distracts from these genuine issues. By focusing collective fear on phenomena that present minimal danger, society risks diverting resources and attention away from the very problems that demand sustained and coordinated response. In this sense, the greatest threat posed by the comet swarm is not physical but psychological. The spectacle of 7 bright visitors and 1 interstellar stranger may tempt us into narratives of doom, but the true responsibility lies in directing our attention to the risks we can measure, understand, and address. Sensational claims about cosmic dangers must be held to standards far higher than those applied to casual speculation about curious coincidences. When voices insist that our comet swarm heralds civilization-ending catastrophe, such arguments require more than vague references to suspicious timing. They demand specific mechanisms, quantified probabilities, and independently verifiable evidence. Without these, the claims remain echoes of human anxiety rather than reflections of astronomical reality. The scientific method exists precisely to navigate such uncertain territory. Through hypothesis testing, statistical analysis, and the scrutiny of peer review, science separates legitimate concerns from unfounded fears. This framework protects us from mistaking psychological pattern seeking for physical threats. Emergency preparedness agencies employ this same discipline. They maintain sophisticated monitoring systems capable of detecting space weather hazards long before they reach critical thresholds. If comet activity or heightened solar conditions genuinely threatened the integrity of power grids, satellites, or communication systems, these agencies would sound the alarm with unmistakable urgency. The silence of such systems in the face of current events speaks volumes. Professional risk assessors, armed with the most complete datasets available, report no extraordinary threats requiring emergency response. This absence of official warnings underscores an important truth. Genuine risks from space weather are well understood and carefully tracked. Solar storms can indeed disrupt technological systems, but their mechanisms follow predictable electromagnetic principles. Power grids can be shielded, satellites can be placed in safe modes, and flights can be rerouted when forecasts predict severe geomagnetic disturbances. The year 2025 promises an active sun, but it also provides ample opportunity to refine our defenses and to gather unprecedented data about how comets behave under such conditions. The enhanced comet activity of this unusual year represents a gift to both science and public imagination. Multiple bright objects streaking across the heavens will inspire new generations of observers while providing professionals with valuable data about solar system dynamics. These benefits far outweigh the risks, which remain minimal. The true hazard lies not in the comets themselves, but in the way unfounded fears can overshadow legitimate curiosity and obscure educational opportunities. Responsible science communication must therefore strike a careful balance. We must acknowledge uncertainties honestly because some aspects of comet behavior remain unpredictable, while at the same time maintaining perspective. Unexplained does not mean threatening. The universe produces mysteries routinely, yet the vast majority of them pose no danger to human civilization. Scientific progress depends on investigating anomalies with disciplined methods, not on surrendering to fear-driven narratives. The doomsday comet scenario reveals more about the human mind than about the cosmos. Our brains, honed by evolution to detect patterns, instinctively interpret clusters of unusual events as coordinated threats. This instinct becomes particularly pronounced during periods of social stress, when populations long for explanations that give shape to their anxieties. Yet the universe does not arrange itself around human fears. Comets follow gravitational trajectories that can be calculated with precision. Solar storms follow magnetic cycles that can be forecast statistically. Space weather operates according to electromagnetic principles that can be measured, modeled, and mitigated. The cosmic clockwork continues its operation with impartial regularity. To understand that rhythm is to find reassurance, not fear. It provides practical protection for our technologies, but also a profound satisfaction that comes from recognizing our place in a universe governed by order rather than omen. That perspective is more enduring than the fleeting thrill of imagined doomsday. The most elaborate conspiracy theory surrounding our seven comet phenomenon paints the heavens as the opening act of a cosmic deception. According to this narrative, humanity is not merely observing an unusual astronomical coincidence, but witnessing the first stage of an extraterrestrial invasion disguised as natural celestial events. In this scenario, 3I Atlas functions as the command vessel, orchestrating a fleet of objects that present themselves as ordinary comets while secretly preparing for reconnaissance, surveillance, and eventual occupation of our solar system. This invasion hypothesis demands technological sophistication of a scale that staggers human imagination. Each alleged probe would require camouflage so advanced that it could flawlessly mimic the appearance and behavior of natural comets. Spectroscopic signatures, outgassing patterns, orbital elements, and even light curves would all need to replicate the precise characteristics of icy bodies formed in the Oort cloud billions of years ago. Such deception implies not only engineering brilliance but also an intimate knowledge of how human astronomy operates our instruments, our detection thresholds, and our expectations of natural comet behavior. Consider the spectroscopic challenge. Modern observatories can detect molecular species with astonishing precision, identifying not only the presence of water, ice, carbon dioxide, methane, and other volatiles, but also subtle isotopic ratios that betray the environment in which those compounds formed. For an artificial probe to pass such tests, it would need to carry a carefully constructed chemical mixture indistinguishable from primordial solar system matter. Any deviation would raise red flags among planetary scientists. The outgassing behavior that gives comets their luminous tails adds another layer of complexity. Natural sublimation arises as sunlight penetrates porous crusts, releasing gases and dust along fracture lines in patterns determined by a nucleus's irregular shape and internal composition. To mimic this convincingly, an engineered comet probe would need mechanisms capable of reproducing sublimation-like jets in ways indistinguishable from geological randomness. Even more challenging, its activity would need to follow the thermal physics of solar heating exactly, varying predictably as heliocentric distance decreases. Photometry offers another test. Astronomers monitor brightness variations over time, creating light curves that reveal rotational periods, surface irregularities, and occasional outbursts as buried volatile pockets rupture. Natural comets rarely show smooth, predictable variations. Instead, their behavior is messy, chaotic, and irregular. Artificial constructs, unless specifically engineered to mimic such chaos, might betray themselves through anomalous periodicities or suspiciously controlled variation patterns. Sustained observation campaigns are already underway, searching for exactly these kinds of subtle anomalies. The orbital challenge remains perhaps the most formidable. Each of our 7 traditional comets follows a path that can be traced back through millions of years of gravitational evolution. Their orbital elements bear the fingerprints of planetary encounters and perturbations consistent with natural origins. For an advanced civilization to introduce artificial objects indistinguishable from such natives, they would need to launch them from appropriate regions of space thousands or even millions of years ago, ensuring their arrival precisely in the 21st century. Such logistics strain credibility. Discovery histories provide additional context. These comets were not new arrivals, suddenly appearing in 2025. NEAT, Lehman, and the Atlas surveys recorded them years or even decades ago, documenting their orbits and predicting their current approaches with accuracy consistent with natural long-period bodies. If they were freshly inserted probes masquerading as comets, astronomers would have noticed discrepancies in orbital solutions. Yet the records show nothing but the consistency expected of real celestial mechanics. Communication provides another line of inquiry. Coordinating a fleet of alleged invasion probes would require data exchange, radio signals, laser pulses, or other forms of electromagnetic communication. Projects within the Search for Extraterrestrial Intelligence community have spent decades monitoring the sky for such transmissions, operating highly sensitive radio telescopes across multiple frequencies. While analysis continues, no unusual signals have yet been detected in association with either 3I Atlas or its supposed cometary companions. The absence of detectable communication does not absolutely disprove the invasion hypothesis, but it does make it increasingly implausible. Sustained fleet coordination across astronomical units of distance would require power levels and repetition rates that our instruments should be able to detect. Stratégique logique also raises difficult questions. If an advanced civilization possessed technology capable of interstellar travel, precision navigation, and flawless comet mimicry, why would it choose such an elaborate and risky disguise? Why not arrive openly, with technology that so clearly exceeds ours that deception would be unnecessary? Why risk discovery through imperfect camouflage when overwhelming capability could achieve objectives more efficiently? From a cost-benefit perspective, disguising war machines as comets seems far less plausible than alternative strategies. Invasion narratives gain traction not because they rest on solid evidence, but because they satisfy deep-seated psychological needs. They provide agency behind coincidence, narrative behind uncertainty, and drama behind dry orbital mechanics. They allow humanity to cast itself as the protagonist of a cosmic story rather than the observer of statistical oddities. Yet when examined through the rigorous lens of physics, spectroscopy, photometry, and orbital mechanics, the invasion scenario collapses under its own weight. What remains is not proof of alien deception, but a reminder of how easily human imagination fills cosmic silence with tales of power, fear, and wonder. Why would a civilization capable of interstellar travel choose subterfuge when a direct approach could accomplish reconnaissance more efficiently? The invasion hypothesis stumbles on this basic strategic paradox. Camouflage offers no practical advantage when the supposed target human civilization possesses no defensive capacity against interstellar technology. If an advanced species could cross the gulfs of space, wield propulsion systems beyond our current imagination, and coordinate across light years, then the notion that such visitors would need to disguise themselves as fragile comets stretches credibility beyond reason. The resource investment compounds the problem. Conceiving and launching not one but 7 camouflaged probes, plus a coordinating command vessel, would demand energy budgets that dwarf the total economic output of human civilization by orders of magnitude. A society able to absorb such costs would wield technological superiority so overwhelming that deception becomes strategically irrelevant. Why bother hiding behind cometary disguises when no resistance exists to require concealment in the first place? The invasion scenario also assumes hostility without evidence. None of the objects we are tracking exhibit behavior inconsistent with natural origins. Pan-stars, Swan, Stereo, Atlas K1, Atlas G3, Lemon, and Neat all move along trajectories that conform to the mathematics of long-period comets, their orbits shaped by gravitational encounters over millions of years. 3I Atlas itself follows a hyperbolic departure path that will carry it permanently beyond the solar system, a one-time visitor, not a scout laying foundations for occupation. A true invasion force would hardly announce its arrival through a trajectory of permanent exit. The psychological appeal of invasion narratives reveals more about ourselves than about the objects under scrutiny. In an age marked by rapid technological disruption, intensifying competition for resources, and a growing sense of diminished human agency, it is easy to project anxieties onto the sky. Unusual astronomical coincidences become canvases for fears of powers operating beyond human control. Fiction bleeds into interpretation, and the silence of the cosmos fills with imagined fleets. But speculation about extraterrestrial intentions cannot substitute for empirical evidence. The invasion hypothesis requires positive proof, materials inconsistent with natural origins, maneuvers beyond sublimation, driven thrusts, or patterns of coordination that exceed the bounds of chance. None of these signatures has been detected. Spectroscopic studies reveal molecular compositions entirely consistent with icy bodies from the outer solar system. Orbital analyses align with long-term gravitational dynamics, showing no anomalies suggestive of artificial course corrections. Brightness variations and tail development match well-understood physical responses to solar heating, not controlled activity. Extraordinary claims demand extraordinary evidence, and the burden of proof rests with those proposing radical interpretations. The absence of artificial signatures does not prove impossibility, but it does heavily favor conventional explanations. Current observations provide no support for the idea that our comets or the interstellar visitor among them are anything other than natural bodies. Professional astronomy takes such questions seriously. Monitoring networks track unusual objects systematically, searching for anomalies that might hint at artificial origin. Protocols already exist within the scientific community for evaluating potential extraterrestrial artifacts, balancing openness to discovery with rigorous skepticism. If genuine artificial characteristics emerged, unexpected isotopic ratios, non-gravitational course corrections inconsistent with known processes, or communications that bore unmistakable hallmarks of intelligence, they would not be ignored. They would be tested, retested, and debated under the most demanding standards of evidence. The investigation continues. As 3I Atlas approaches perihelion, closer observation will sharpen our understanding of its composition, structure, and behavior. If subtle artificial signatures exist, higher resolution data may reveal them. If coordination exists between the interstellar visitor and the 7-comet swarm, correlations may yet appear in timing, tail activity, or orbital anomalies. Science is not closed to the possibility of surprise. It simply requires evidence strong enough to outweigh the null hypothesis of natural origin. Science fiction scenarios serve a purpose. They stretch imagination, explore possibilities, and prepare conceptual frameworks for the day when extraordinary evidence might truly appear. But narrative power cannot be confused with empirical truth. Entertainment value does not justify presenting speculation as fact. The universe offers enough authentic mysteries, statistical anomalies, interstellar visitors, and the dynamics of solar activity without requiring us to invent additional puzzles based on fear or wishful thinking. Our 7-comet swarm remains a legitimate anomaly, worthy of investigation and sustained attention. Yet investigation must follow the trail of evidence, not leap ahead to predetermined conclusions about invasion fleets and cosmic conspiracies. Wonder and curiosity survive best when grounded in rigorous method, not untethered speculation. As we prepare to synthesize our findings, let us remember, scientific rigor does not extinguish wonder. The very tools that guard against fantasy are also the ones that allow us to recognize genuine discovery when it finally arrives. The cosmos may yet surprise us in ways that challenge every assumption, but those surprises will emerge through careful observation, precise measurement, and evidence strong enough to withstand skepticism. The clockwork of the heavens continues, indifferent to human fears. Whether the patterns we see reveal deeper truths or mere coincidence, the answers will come not from speculation but from the data written in starlight. After months of patient inquiry, tracking orbital mechanics, running statistical tests, and scrutinizing every conceivable link between 3I Atlas and the 7-comet parade, the weight of evidence points toward a conclusion that is both reassuring and remarkable. What we are witnessing is not the signature of exotic coordination or extraterrestrial intent, but an extraordinary natural convergence. The swarm of 2025 represents a genuine statistical clustering, striking precisely because such alignments occur rarely enough to feel almost orchestrated. Pan-stars, Swan, Stereo, Atlas K1, Atlas G3, Lemon, and Neat each follow paths carved by gravitational influences set in motion millions of years before human beings looked up and wondered. Their present convergence is the outcome of cold, celestial mathematics, not deliberate design. Yet to call it mere coincidence understates the grandeur of the spectacle. The universe has arranged a festival in the skies, an alignment that offers unparalleled opportunities for scientific study, cultural engagement, and a renewed sense of wonder. Into this theater enters 3I Atlas, the interstellar wanderer that transforms an already extraordinary year into something historic. Here, for the first time with clear documentation, we are able to watch a comet-like object forged around another star respond to the heat of our own Sunday. Ice and dust, preserved for millions of years in interstellar exile, now vaporize before our telescopes, creating tales that reveal alien chemistry in spectral lines etched across our detectors. This is a messenger from another stellar nursery, carrying in its composition the fingerprints of processes we can only glimpse from afar. The timing of its arrival, coinciding with our most comet-rich year in memory, continues to intrigue researchers. Yet the evidence so far suggests coincidence rather than causation. Sometimes the cosmos creates patterns that feel meaningful through purely natural processes, reminding us that coincidence and significance can coexist without invoking hidden mechanisms. The investigation has uncovered no shared orbital relationships, no anomalies of behavior, and no correlations in timing that exceed the thresholds of statistical expectation. Each comet retains its individuality, a solitary traveler responding to solar gravity and heat according to its own unique structure. Far from diminishing the importance of 2025, this conclusion heightens it. Multiple bright comets appearing in a single observing season provide a comparative laboratory rarely available in the history of astronomy. Scientists can track how different sizes, compositions, and orbital geometries respond under similar solar conditions, advancing cometary physics in ways that isolated case studies cannot. Solar maximum adds another layer of richness, as coronal mass ejections and high-speed particle streams reshape comet tails, creating natural experiments in space weather science. The same storms that complicate satellite operations sculpt luminous arcs and disconnections that photographers capture in breathtaking detail. Amateur astronomers play a central role in this investigation. High-quality digital imaging has become so widely accessible that hundreds of observers across the globe contribute continuous monitoring, providing a distributed coverage network no single observatory could replicate. Their photographs and light curves form a living archive, data that professional astronomers analyze alongside their own observations. This collaborative approach multiplies our capacity to capture fleeting phenomena, ensuring that 2025 will be remembered not only for its spectacle, but also for the depth of its record. The broader cultural significance is equally profound. Public fascination with the comet swarm has created rare teachable moments about how science works. By clearly distinguishing between established fact and speculative possibility, researchers have been able to model the process of critical thinking in real time. The investigation shows how extraordinary claims are tested against evidence, and how statistical anomalies can inspire curiosity without descending into fear. This is science education at its most powerful, emerging not from classrooms but from the sky itself. The absence of exotic connections does not close the door on discovery. Continued monitoring may reveal subtleties that current analysis has overlooked, or closer approaches may uncover signatures beyond present detection thresholds. Science progresses incrementally through refinement of instruments and methods, with breakthroughs sometimes hidden in data patiently accumulated over years. What 2025 offers is not a warning of invasion or catastrophe, but a celebration of celestial mechanics in motion, a chance to study, to marvel, and to be reminded that even coincidences can carry meaning when illuminated by the light of understanding. The statistical clustering that defines the year 2025 may ultimately illuminate processes that unfold across timescales far longer than human memory. If similar groupings occurred in the distant past, or emerge again in predictable cycles, they could point toward deeper structures in solar system dynamics, gravitational resonances that nudge objects into alignment, solar cycle effects that subtly alter trajectories, or other periodic influences that govern comet arrivals over spans of millions of years. The pattern we witness now might be a fleeting coincidence, or it could prove to be part of a rhythm written into the architecture of the solar system itself. Professional astronomy will continue its patient work, cataloging orbits, refining predictions, and testing every anomaly against the most demanding standards of evidence. Every unusual object, whether homegrown comet or interstellar visitor, is scrutinized not only for what it is, but for what it might reveal about processes beyond current understanding. This vigilance includes the willingness to consider exotic possibilities, artificial origins, unfamiliar physics, even traces of intelligence, while applying the rigor necessary to distinguish legitimate anomalies from the statistical noise that emerges inevitably from vast datasets. The implications of this investigation reach far beyond the narrow question of whether 3I Atlas is connected to the 7-comet swarm. What matters equally is the process itself, a demonstration of how scientific inquiry addresses extraordinary hypotheses without being consumed by them. In an era when social media amplifies speculation faster than careful analysis can respond, this balance between curiosity and skepticism is more vital than ever. The scientific community carries responsibility not only to provide accurate information, but also to acknowledge uncertainty honestly, resisting the temptation to compete with sensational narratives through exaggeration or premature conclusions. The 2025 Comet experience also highlights the enduring human tendency to transform objective events into subjective stories. Pattern-seeking brains instinctively weave meaning into coincidence, turning a convergence of comets into a cosmic message. This isn't inherently misguided. For millennia, people have drawn inspiration, comfort, and caution from the heavens. What matters is the conscious separation between the facts recorded by our instruments and the interpretations we craft in response. Modern astronomy supplies tools capable of distinguishing between true anomalies and apparent patterns generated by random variation. With these tools, we discover that the universe already contains wonders greater than any speculative fiction. Interstellar travelers that cross unimaginable gulfs, solar storms that sculpt comet tails into luminous banners, gravitational dances that persist across eons. As this investigation draws to its close, we are left with a cosmos that is at once more comprehensible and more mysterious than the stories we tell about it. The universe obeys laws that can be tested and understood through careful observation. Yet those same laws produce phenomena so strange and unexpected that they continuously stretch human imagination. The message of the 2025 swarm may be simple. The cosmos does not need embellishment. 7 independent comets arriving together by natural processes, coinciding with an interstellar visitor on its one and only passage through our system, is remarkable enough on its own terms. The educational value of this moment extends far beyond astronomy. Learning to distinguish correlation from causation, to weigh claims against evidence, and to maintain a sense of wonder while insisting on rigor, these are intellectual skills that serve society in every domain. Future generations may look back on 2025 as a watershed, when improved survey capabilities combined with global networks of communication to transform ordinary astronomical monitoring into a cultural phenomenon. Millions of people, many encountering serious astronomy for the first time, found themselves drawn into conversations about probability, evidence, and the nature of scientific knowledge. In the end, the swarm's greatest message may be less about comets than about ourselves. Humanity has built tools capable of detecting interstellar visitors, tracing orbital histories across millions of years, and testing extraordinary claims against the unforgiving mathematics of statistics. That achievement, the product of curiosity and collaboration across cultures, deserves celebration alongside any celestial spectacle. The universe may not be sending us messages through coordinated arrivals, but it continues to provide opportunities for discovery, rewarding those who watch carefully with deeper understanding. Our investigation concludes where it began, with wonder at unusual timing, with respect for rigorous analysis, and with appreciation for a cosmos that offers enough authentic mystery to engage human curiosity for millennia to come. Hypotheses tested, evidence weighed, wonder preserved, the stage is set for the next questions waiting beyond our present horizons.